Welcome to this video course, Practical Process Control. The aim of this video course is to try to reduce the gap between theory and practice. At the end of this video course, you should be able to design a control system for a simple process. You will be able to understand the process. You'll be able to design a control structure in a systematic way, and you'll be able to tune the underlying controller, either a PID controller or an internal model controller. After some real life experience in industry, of course there is nothing that goes above practical experience, you should be able to extend the knowledge that you have acquired in this course to become an expert in designing control systems for complex production lines. Let us have a look at what is on the menu. I will start with an introduction, and the idea is to introduce or reintroduce some basic concepts and notations. We'll also look at the paper production process, and we'll use it to present some of the topics that will be discussed in this video course. In the second section, we will review some system theory. Of course, here the pace will be rather high because this material has been covered in the course Signals and Systems. Some concepts might actually be new to you. For example, the concept of internal stability and the peak sensitivity robustness margin. The next section is dedicated to process behavior. We will start things very simply by considering the gain process, static gain, and we will gradually complexify the process. We will study these processes both in the time and the frequency domain. Knowing the process is knowing its behavior, its interaction with other processes, the type of disturbances that are acting, input and output disturbances, the non-linearities that are present in the process, and constraints. Process knowledge has huge implications on the control structure that will be used and the type of control. PI, PID, internal model control, and so forth. In section 4, we will introduce a systematic way to construct a control structure. We'll do this for a very simple process, but given a bit of experience, you can use this procedure to design process control systems for complex production lines. The main ingredients will be cascade control, feed-forward control, override control, ratio control, split range control, and mid-range control. Section 5 will focus on the PID controller. Notice that this section on the PID controller comes very late in the course, but this is done on purpose. Before we can tune the controller, we should understand the process and make sure that we have chosen the appropriate control structure, because we cannot compensate an inappropriate control structure by tuning. The focus in this section will lie on understanding the PID controller, and will propose several tuning methods. We will see that choosing a controller that is not the PI or PID controller comes with certain difficulties and costs. In practice, the PID controller is therefore recycled very often. Typical examples are processes with digital MVs, processes with dead time, with complex responses such as an inverse response, for instance, nonlinear processes, and multivariable processes. This recycling of the PID controller will be the topic of section 6. In big production lines in the paper, steel, foil, food industries, PI and PID controllers are used very often. When they are not used, there is a big, strong possibility that an internal model controller or IMC controller is used. The IMC controller is the topic of section 7. We will construct it from scratch so that you really understand how the controller originates. We will make the link with one of the PID tuning methods of section 5. Section 8 will not be covered in this video course. It applies IMC PID tuning to the DC motor, so you'll find applications for position and speed control in single loop and cascade applications. Section 9 is simply a dictionary with most of the control terminologies in 4 languages: English, French, Dutch and German. These are the main references that I've used to compile the slides and to compile this video course. I should also thank all the people I've worked with in the 10-year period when I was working at Siemens as a control engineer. These people have learned me quite a lot about control in practice. I also want to mention 2 ACT training courses. The first one, applied control techniques, the second one, model-based control, that I have followed in the early 2000s when I was at Siemens, and these 2 courses have most probably triggered and inspired me to teach in control theory. This is a nice reference because this book can be used without charge to learn about process control. You simply have to click on the link to access the book, and the example of the preheating furnace has been drawn from this reference. I like the 2 references in bold quite a lot. The first book covers single loop control, and the second book extends the concepts beyond single loop control, as you can see. These 2 books treat process control exclusively in the time domain, and this is perfect for you if you're allergic to the Laplace transform. These books are a good help if you want to discover more and go beyond what you see in this course. Notice that I have borrowed the title of the first book to name this course: Practical Process Control. This is the control system configuration that we'll consider in this course. It's a control system configuration that is very similar to what you have seen in previous courses. For example, the course of Fundamentals of Control Theory of my colleague David Rochard. The output of the controller MV is constructed from the control error. The control error is, well, set point minus the process value, and over here you can see the feedback part. Here you have the process. We'll assume that there is an actuator. A typical example of an actuator is, for instance, a control valve. Here we have the process dynamics, and of course your controller is acting based on an output that is constructed by a sensor. In the next slide, and very often in this course, we will assume that the actuator effects are included in the process and that the sensor dynamics are flat and 1, so that we can discard their effects. There are, of course, disturbances acting on the process. Here, output disturbances, and they will be denoted dV, and there are also load or throughput disturbances, and we'll denote them dL. In the next few slides we'll put them simply at the input. So the acronyms that you see here vary from one reference to another. For instance, in another reference book you might see different acronyms, and also if you read the documentation that is related to a control system, you might find different acronyms. In reality, the controller has to be implemented on a PLC, on a processor, so it needs to be discretized. What you have to do here is to consider the fact that, well, this signal over here that is analog has to be converted to a digital signal, so you have to take into account quantization, you have to take into account the digital coding. At the output here, the signal is digital, and you have to consider the digital to analog conversion, and very important, well, the hold mechanism, which is very often a zero order hold mechanism. In this course, we'll consider a controller that is C of S. Okay, very often we'll have here simply a PID controller, but this C of S will come from a so-called analog design, right? And in the background, of course, there will be a C of Z that will come from the discretization of this controller. We'll assume here that the effects of the zero order hold mechanism and the other effects related to analog to digital and digital to analog conversions are neglectable. So this means that you can do this for a TS that is small with respect to the main time constant. So this is the hypothesis that we'll take in order for the zero order hold mechanism not to have too much effect. Another thing that you could say is that, well, you're working with a controller C of S, for instance a PID. In the background, of course, it's discretized, but you're tuning the PID controller on the actual system. And if you're doing that on the actual system, well, the zero order hold effects and the effects of the two conversions are automatically taken into account. So this is the control system configuration that you end up with. The process here, well, it also includes the effects coming from the actuator or the sensor. Here the controller, in our case the controller will very often be a PI or PID controller. SP, set point, is the signal we want to track. PV is the output signal, right? It's the control signal. Over here you see the feedback part. E is the control error, set point minus PV, and on the basis of E, the PID control algorithm will compute an MV. There are two types of disturbances. Disturbances at the output, denoted DV, and load disturbances. Disturbances at the input or disturbances on MV, denoted DL. And with the lowercase letters, you see here acronyms that are sometimes used in the course, or acronyms that refer to acronyms used in previous courses. In practice, there are two important types of control problems: disturbance rejection problems and set point tracking problems. In a disturbance rejection problem, the set point is constant or hardly ever changes. The main goal of the controller is to reject the disturbances, the output disturbances and the load disturbances. Well, a typical example of a disturbance rejection problem is the temperature control of a room. The set point, the temperature set point, hardly ever changes, but the controller has to reject disturbances, for instance due to people coming in and out of the room and disturbances coming from the outside temperature. Set point tracking problems are problems where the controller is designed to follow a reference or set point or trajectories as closely and as fast as possible. So for instance, the closed loop setting time is an important factor. Tracking typically occurs during operating point changes. Just-in-time production plays a more and more important role so that operating point changes occur more often, and that the set point tracking plays a more important role. People have a tendency to associate the controller with set point tracking, but we'll see that the disturbance rejection capabilities of the controller should not be neglected. Control loop optimization is the art of finding compromises between disturbance rejection performance, tracking performance, but also robustness. Robustness is the sensitivity of the control performance to changes in the process. The control effort or control energy is also of concern, as this control energy is related to the final cost of the product and to wear and lifespan of the actuators. In this course, we will represent a system or a process by the letter P, so we'll use P of S. And in previous courses we might have used H of S because we wanted to put the focus on the fact that H of S is the Laplace transform of the impulse response. In this course we'll put the focus on the fact that P here is the process. In the same fashion we'll use the letter C to denote a controller, although very often the controller that we'll tackle is of course the PID controller. A multivariable vector signal will be denoted in bold, so here y of t with the y in bold is a vector signal, whereas y of t without the bold is a scalar signal. Of course, the focus of the course lies on SISO systems, so single input, single output systems. So the process will be denoted by the letter P, as I've said before. At the end of the course, we'll speak a little bit about multivariable systems, so multiple input, multiple output systems, and there the process will be described by a P in bold. There are several control modes associated with the controller, and as I said before, this controller will very often be simply a PI or PID controller. Well, the first choice that you have is to put this controller in automatic or in manual mode. In manual mode, the controller output MV is directly manipulated by the operator. And this can be done, for instance, by changing a value MV_man in the human-machine interface to directly influence the process input. In manual mode, the control algorithm, and very often the PID control algorithm, will be bypassed. In automatic mode, the controller output is dictated by the control algorithm, typically, as I said, a PID control algorithm. Well, when switching from manual mode to automatic mode, the control algorithm output might be different from that of the manual output. So you have to organize a bumpless transfer from manual to automatic, and this means that the automatic output must track the manual output in manual mode in order to prevent integrator wind-up and also in order to organize this bumpless transfer. We'll see this later in the section on integrator wind-up. When in automatic mode, it's a good idea to make sure that this manual value MV_man tracks the output of the controller MV_auto, so that when you go to manual mode, you have access here to the last available MV in automatic mode. This will ensure a bumpless transfer, and if needed, the operator can choose to change the value MV_man. The second control mode has to do with the set point. So this control can either be in external set point mode or in internal set point mode. Sometimes you find other names such as remote set point and local set point. So external set point mode corresponds to remote set point mode, and internal set point mode corresponds to local set point mode. In external mode, we speak about an external set point. This means that the set point of the controller comes from a remote location, from something that is external to the system. For instance, a data bank or the output of another controller, and this is the case, for instance, in a cascade. In internal mode, we speak about an internal set point or a local set point. The operator sets the set point of the controller directly through the human-machine interface. Again, there might be problems when switching from one mode to another. So for instance, from external set point mode to internal set point mode. We have to organize a bump list transfer from external to internal set point. So when you're in external set point mode, the internal set point must follow the external set point, so that when you go to internal mode, well, the internal set point coincides with the last external set point. There might also be problems when switching from internal set point mode to external set point mode, for instance in a cascade. When in internal mode, the external set point should be chosen appropriately, and this will be discussed in the section on cascade control. The third control mode is the output tracking mode or interlock mode. When this binary signal here, track on, is set to 1, then the controller output MV will track the value here, track val. This is a signal that can be chosen by the one that is programming the control algorithm. When track on is set to 1, the control algorithm is inactive, and as I've said, MV is equal to track val. I said that the control algorithm is inactive, but this has to be done in the proper way in order to prevent integrator windup. We'll see this later in the section devoted to integrator windup, in which we implement a controller that has this output tracking mode or interlock mode. An example of output tracking is the following. Assume here that there is a measurement PV that comes from a sensor, and that this sensor provides a binary flag to tell you if the measurement is okay or not. So if PV knock here is 1, this means that the measurement is not valid. Well, if this sensor is giving you this flag, PV knock is equal to 1, this means that the process value measurement is no longer valid, and of course you cannot use it for control. So what you should do is freeze the controller. This can be done as follows. You connect the PV knock signal flag coming from the sensor to track on, and you connect MV, the output of the controller, to track val. What will happen when the sensor flags a signal, a measurement that is wrong? Well, this one will go to 1 and MV will track itself, so that you have here at the output the last value that you had in automatic mode. Okay, so the controller is frozen with the last active value of NV. The controller is locked, and of course in the human machine interface there should be a warning for the operator to tell him that there is something wrong with the measurement, but at least nothing goes wrong in the sense that the controller is now locked. There are many reasons why a controller can be locked. So usually there will not be one track on binary signal, but several of them. So there will be several track on I signals with corresponding track val I. Track on 1, for instance, has priority over track on 2, which has priority over track on 3. So if several of the track on I are set to 1, MV will follow the activated track val I with the highest priority. Usually the reason why a controller is locked is displayed in the faceplate of the controller in the human-machine interface. As you can see over here, track val is equal to MV, but this is only one of the many possibilities, as we will see later in the course when we consider cascade control and output tracking in that particular case. I will now introduce the Siemens Simatic PCS7 system. You will find more information about it on the net, and this PCS7 DCS system can be used to automate one or several large production lines. What I will do is use a version 8, so a slightly older version than the version 9 that is now available, to illustrate some of the concepts of the course. I will start by illustrating the different controller modes that I've just talked about. What you see over here is the Simatic Manager. It allows you to interact with the PCS7 system, with the actual process, with the controller, and with the human-machine interface. What we will do here is use a 7 PLCsim to actually emulate a PLC, and what we'll do is kind of program or model the system and design a controller for it and a human machine interface in Siemens Windows Control Center. I will now briefly show you what the different components are of the Simatic Manager. Well, first of all, what you can do is introduce the hardware configuration. So you have to choose CPU, right? Here we are working in simulation, so I've just added a CPU. In reality, of course, you'll have to interact with the system, so there might be several CPUs, and of course there will be I/O, so you'll have to choose some of these cards: analog input cards, analog output cards, digital in and digital output cards. Once you have done this properly and that you have compiled things and downloaded to the relevant CPUs, well, you can interact with the actual system. In this section you will find everything that has to do with the programming. Here is the source container. If we have a look, for instance, you will find over here the source code to implement a lead lag system using SCL code. This is a Siemens language called structured coded language. We'll come back to that later in the section dedicated to process behavior. Over here you have the block container with the FBs, so function blocks. They have an instance DBs, FCs just functions, and then DBs data blocks. This looks very similar to what you've seen in other courses, but probably on a system coming from another vendor. What you will see over here is the function block lead lag that will implement the lead lag system, and it has resulted from the compilation of the code that I've just shown you before. Here you have the CFC chart folder. CFC stands for continuous function chart, and CFC is a graph editor that allows you to program the entire control software. Well, let us open a few charts. What you see over here is a chart that allows you to implement a process. Remember here that we use PLCsim, so we do not have any actual system. So what we'll do is simulate the system, emulate the system, and you can see that you can do this very easily using this graphical editor. So this is a dead time, and this is this lead lag block FB3 that has resulted from the compilation of the SCL code that I've shown you. As you can see over here, we can construct a simulated process using a dead time, several lead lag systems, a resonant part, and some noise. These blocks are running with a certain sampling interval. but we'll come back to that later. We can have a quick look at the PID controller just to give you an idea of the type of block that is used in PCS7. It's much more than a block with simply a few inputs and a few outputs, but this will become clear later in this course. Once the program has been compiled and downloaded, I will not do it right now, you can interact with the system directly in CFC and see the different variables. So for instance, this is my lead lag system, and here you see the input and the output. Instead of interacting with the system using a CFC, what you can do is also design your human machine interface, and for Siemens this is done using WinCC, so the Windows Control Center. So what you can do is compile everything so that the variables become available in the WinCC Control Center, and what you can then do is design pictures of the type that you see over here to generate a nice human machine interface. So we will stop this because this will take too much time. We can have a look at one of these images, for instance this one. Here you can design your interface with the actual system, so the human machine interface. Here with Siemens it's done using the graphics designer that is associated to the Windows Control Center WinCC. Very often what is done is that there is a drawing of the PNID so that the operator can see where he is interacting with the system, and usually faceplates are used, I will show you later, to interact, for instance, with the PID controllers. There are curves and there are possibilities to interact with certain parameters, and if I go and have a look at the properties of this one, you will see here that there is a link with a variable that has been obtained using this compilation procedure. This is how you make the link with what is happening in the actual PLC. So this is how it looks like in real life in the human machine interface. So here, Windows Control Center. This is for the preheater example that we'll treat later on in the course, so I will not go too much into details, but you can see here the trends. You can interact with the system, so I can, for instance, change the set point. So you can see that the set point is decreasing. Here there is a ramp on the set point, so it does not decrease directly, but you will see that it will stabilize at 60, and you can have a look at the parameters. We will not go into the details of this system for the moment. This is for later. What I want to illustrate are the controller modes that we have talked about previously. So this is the WinCC interface with the process that we have programmed. So in this way we can change the emulated process. In this case it has a dead time of 2 seconds. There are two first order systems, as you can see, because here the lead time constants are 0. We'll come back to that later. The first order system has a time constant of 10 seconds and the second one of 3 seconds, and we have added some noise. Here we can interact with the process, with the controller, using this interface, and as you can see here, this controller is in automatic mode and internal set point. So this means that since we are in internal set point, the operator, in this case me, can change the set point locally. So we can, for instance, change the set point to 60%. Well, percent degrees here because it's a temperature controller. As you can see here, in blue you have the set point, in green the process value, and here in brown the output of the controller. So what you can do also to illustrate here the concept of automatic and manual mode is go to manual mode. Observe here that the manipulated value MV is fluctuating. When the controller will go to manual mode, the last active value in automatic mode will be selected and will have a bumpless transfer. This is illustrated now. As you can see, the value is fixed to its last automatic value. I am in manual mode and I can change the manual value. So now I'm interacting directly with the process because I am imposing the input of the process. So I have just changed the manual value to 40%, and as you can see, the system is interacting with that. So I hope with this that you see the difference between automatic mode and manual mode. Well, in order to illustrate the concepts of internal mode and external mode and output tracking, I'm going to use another system here, and it's a cascade system. I will not go too much into the details because this process will be used when I will be talking about cascade control. But it suffices to say here that you have an outer loop and an inner loop, or a master loop here and a slave loop. Okay, so the master loop is controlling the temperature over here, and it is setting the flow of fuel here, and the fuel flow is controlled using this slave controller by acting on the control valve over here. So let's open the two control faceplates. So as you can see here, I have the master and here I have the slave, right? And you can see here that the slave controller is in external mode. It is impossible to change by clicking over here the set point of this controller, because this slave controller receives the set point from the master controller. You can see it over here. The manipulated value of the master controller is the set point of the slave controller. So what we can do now is change and go to internal set point mode, and you will see here that the set point will change color, and it is also possible now to go, for instance, to a set point of 5 liters per minute. Okay, so we are in internal set point. So this means now that the link between the manipulated value of this controller and the set point of this controller has been broken. Okay, we will see when we talk about cascade control that you have to do something about this controller. If you do nothing, you will see that there will be wind up of the integral action. So what you will have to do is make sure that this controller goes into tracking mode or interlock mode, and you can see that it has done this. You can see here tracking mode and the T appearing here. Okay, so the PID control algorithm has become inactive, and the output of the controller is actually, in this case here, the process value of this one. We will see this later. You can see here that the manipulated value is now tracking the process value, and this one is in tracking mode. If I go to external mode again, right, this controller will be acting again, will be controller, and you will see here that this tracking will be disappearing. Again, here we have this cascade control that is active, and what you see over here is indeed again the set point. Well, using this faceplate that you've seen before, it is possible to interact with the PID controller, here a temperature PID controller. There are similar faceplates for control valves and for motors. If we click on the faceplate, this is what you obtain, and this part you have already seen, but you can also of course change the control parameters. Okay, so the parameters of the PID, so this is the PID control gain, the integral time constant and the derivative time constant. We'll come back to that later. You can also set limits, right? And if PV goes outside these limits, an alarm is generated. Here all limits have been deactivated except a warning and an alarm on the maximum value of PV. As you can see now, the process value is at 60. So if we, for instance, put a warning level of 40 degrees, we should obtain an alarm. As you can see over here, it's clearly shown that the PV of this controller has exceeded the warning limit. Assume now that the operator is looking at some other part of the process. It is clear from this warning that there is a problem, and he can click and see where the problem is coming from. Of course, then he has to do something about this problem. For us it's rather easy. We put the old value and the problem is solved. In reality, of course, things will become a little bit more difficult, and then he can quit the alarm. It is possible to consult the list of previous alarms, and this is what you obtain. Of course, here there is only one type of alarm, but you can see that this high warning limit violation has occurred several times. The last time that it has occurred, it was active for 35 seconds and it was quitted after 43 seconds.